glimpse of true beginning. The first thing we can see is a hot, dense, pent-up universe already taking its first step toward evolution. This is the Big Bang. Expansion pulls over our universe, and the forces of nature unfold. As each of them seeks its own balance, they drive a flash of faster-than-light inflation. Patterns of quantum static freeze and scale up with space, forming large-scale temperature differences. And beginning in the coolest regions, energy settles into stable matter. Light is everywhere, but it's trapped in this fog of unbound particles. Scattering photons push visible matter outward, but most matter can't be pushed against or even seen. This dark matter comes together, concentrating the pull of gravity against the push of light. In a cosmic tug of war, gravity and light send waves rippling out across the ocean of particles. Sound waves. Once it's cool enough for stable atoms to form, the fog clears. Light radiates onward across space, abandoning matter or the pull of gravity. And beginning with the overdense wisps of gas left behind by sound waves, gravity compresses tendrils of hydrogen and helium. At such close range, the strong force binding the cores of atoms together overpowers the electromagnetic force, pushing them apart. Subatomic particles scramble and reassemble, forging entirely new elements. During nuclear fusion, some mass goes missing. Some of the energy bound up in matter escapes and explodes outward. A star is born. These early titans fuse heavier and heavier elements together until fusion consumes more energy than it produces. At iron, the delicate balance ends, and the star implodes. Subatomic particles collide, allowing the shortest range force, the weak force, to change their very identities, forming an ultra-dense neutron core. The rebounding supernova unleashes a burst of remixed matter and energy, forging elements heavier than iron and scattering them across space. But this star is not over yet.
Cast out jets of half-formed atoms. In the aftermath, nuclear forces bind them together and settle them into stable identities, forging gold, platinum, and the rest of the naturally occurring elements. What's left behind is something with all the mass of a star, but none of the light. A black hole. So much mass concentrated in so small an area warps the fabric of space-time so that not even light can escape. Around these hulking giants, gravity weaves bright galaxies together and sends them cartwheeling across empty space. We once thought that gravity would pull everything back together again. But empty space isn't empty. Something in space itself is accelerating the expansion of the universe. This dark energy stretches out the space between galaxies, pushing them apart faster than gravity can pull them together. Gravity is only strong enough to bind our galaxy to our closest neighbors, the Milky Way, our continent in an ever-expanding ocean of space.
And on our island, the Milky Way, an oasis forms as one star's graveyard becomes another's mortuary. Our infant solar system inherits star-ripening ice and dust, and on Earth, something very strange happens. Oceans of liquid water, solid continents, and a stable atmosphere are host to another of nature's mysteries. Following the same rule that birth stars and matter, life and consciousness
already uncovered much of the story of where we've come from. And with every discovery, our curiosity expands. Where are we? When and what and why are we? And what's next? The same physics that illuminates the past can tell us the future. In a cosmic moment, gravity will merge the Milky Way with our nearest neighbors. Distant galaxies fade from view as dark energy stretches the space between us. Our cosmic horizon shrinks until we can only see our own galactic neighborhood. And things are changing here too. Stars burn through their remaining fuel and twilight falls over the cosmos. Black holes feast on cooling stars, but not even they will last forever. They evaporate over the eons, leaking their mass away in quantum events at their borders. Nature's craving for balance shreds everything into a chaotic sea of particles. The universe contains just as much energy as when it began. But it's so spread out that no known force can spark something new. This is the end of the story we know.
What happens next depends on physics we don't yet understand.
As with the beginning, we can barely imagine the end.
But we can try. If dark energy continues stretching space faster, the space between molecules, atoms, even subatomic particles, might someday expand faster than light. Each particle will appear as if it's alone in the center of its own universe. The clock is still ticking, but nothing happens anymore. Just time really exists, and every moment looks the same. As the universe stretches beyond our comprehension, the improbable becomes inevitable. Give them enough space and time, and quantum events might jostle reality enough to change the rulebook of our universe, from one of infinite inflation to contraction, or even oscillation. Our story has changed many times since we were awoken to the universe. For all we know, the discovery of new forces might rewrite its end yet again. Only time will tell. Or perhaps time is not so simple as it feels, and our sense of a story with a beginning and an end is too narrow a perspective of reality. The same logic holding our story together contains the far-fetched possibility that our universe is one of many, a chapter in a larger story. Perhaps new universes bud off from ours and blossom into branches of an infinite multiverse. And perhaps in one of them, someone is asking the same questions and telling the same story.